All right, so welcome back for those of you who were at the previous two. Both of them were just like 30 minutes. We were just going over the consumer preferences, budget constraints, and stuff like that. So today we'll just be reviewing choice and utility maximization. So that's something you should have covered like two weeks ago, I believe. So it's nothing groundbreaking, and we won't put too much time into it, but we'll also go over a couple problems from the 2017 midterm exam, which was a Prof Zoo as well. So the first thing we're going to cover is what a rational consumer is, or a rational economic agent. We define this as an individual who chooses their most preferred alternative from those available and feasible to them. When we say feasible, we mean it's affordable, i.e. it's in their budget set, which is the set of affordable bundles. Just beyond that, when we say available, it just means that they actually have the opportunity to purchase it. In reality, you'll see plenty of times where a consumer is not a rational economic agent. However, on these exams, you won't get anything along those lines, so you don't have to worry about that. So they are going to select their best affordable bundles. That's the best bundle for the consumer from the set of affordable bundles given. And of course, they're just trying to maximize their utility. So the first thing we're going to do, and when we see these problems, we're just going to call it the consumer's choice problem. We're going to set up the problem itself. So we're going to suppose that the consumer only consumes two goods, being good one and good two. We'll set up the set or the bundle, and then we're going to move on just defining out. And this is exactly, when I take the exam, this is exactly how I outline it. I write price one, price two, and then I put the income. I put all those details that were given right at the top, and then start solving for the rest of them that I would need to set up the actual budget, or the budget set utility maximization problem. So we'll run through it like that, with the budget set being the price of good one times good one plus the price of good two times good two, which has to be equal to the consumer's budget to actually be maximal or the optimal choice. But of course, it can also be less than, so it just has to be within their affordable, feasible set. So when it comes to actually calculating the best affordable bundle, we're going to be looking for X prime, which is just the optima, or the bundle that has actually been optimized given their constraints, given their utility functions, such that X is at least as good as all of the other bundles or all of the other options for the given utility and given bundle set or budget constraint. So we're going to define that again. X prime is the best affordable bundle. We're going to use budget, price of good one, price of good two as parameters, and then we're going to define both of those as Marshallian demand functions. Is that something he's defined for you all specifically? I assume so.
Yeah.
You'll learn a few different demand functions, but the Marshallian demand function is just the demand for the good as a function of price and as a function of budget. So again, consumer is only consuming goods one and good two. We're going to look at the utility function representing the set of that's at least as good as the consumer's problems. And again, for that, it's the same exact thing every time. We're just looking to maximize the utility for bundle X, such that X is an element of our feasible bundle set. We're also going to be looking at the second part there, which is just maximizing utility such that it's actually affordable. And this is a constrained maximization problem, constrained choice problem. So if you've done Calc 1, Calc 2, you've seen problems exactly like this. The difference now being that we're using economic phrasing, and it's actually two parts instead of just one part. So you have to maximize utility such that it's affordable and such that it's actually within your purchasable bundles. So this is, whenever I do a problem, I set it up visually. I know you guys are going to be taking the exam in person. I assume you're allowed calculators. So if that's wrong, you can update me on that. But if it really helps you a lot, you can do exactly what I did, is just plug that right into your TI-84 and figure out what exactly is going on. That's something I use whenever I run into issues. So if something's not adding right, like if I write down my answer and I'm like, something's completely off here, I'll just throw it into the graphing calculator. That usually helps me visualize the problem. So I always go with that. So again, right here, we just have the visualization of the constraint problem. This is the standard case. So this looks like it's a Cobb-Douglas utility function and just a pretty standard budget line. But we're just looking at the best and difference curve given the budget constraints. So this is our utility curve that is tangent to the budget line and the furthest out. So our best affordable bundle, which is going to be the marginal rate of substitution of goods one and two, is just going to be equal to negative price one divided by price of good two. that's just going to be your slope of the budget line. And that's a very important thing to understand, is that you're going to be able to plug that slope in to a formula for the Marshallian demand function to be able to calculate the point of tangency. So again, of course, it's great to be able to use calculus to solve all these problems. You can just practically plug and chug once you've done enough practice and you understand how to actually write out the information and set up the optimal choice problem. But there are certain situations where you have like a special case and you can't actually do that. So one of the most common ones, at least for our professors do, was just the case of perfect complements. So here we have and I'm going to mispronounce this, a Leontief demand function. Basically, you're looking at the minimum or the lesser of these two functions right here. So we have AX1 being A good 1, and then we have a B good 2. And both of those are going to form an indifference curve. Of course, it's going to have two linear parts to it. They're just going to intersect right here. And when I solve one of these problems, the first thing that I'm going to do is I'm going to write up this function right here. You guys can see my mouse, I believe. So that's going to be good 2 equals A divided by B times good 1. That's because the point of intersection between the utility functions, these two utility functions, are just going to be always on that line. So once you figure that out, the rest of the problem is incredibly easy. You can really just plug and chug the rest of your way through that problem, but it's always going to occur right at that point. And if you're looking at the optimal choice problem, so we have to figure out the point of tangency, we're literally just looking at where this function, x2 equals A divided by B times x1, intersects the budget line. So when you see perfect complements, you should get excited. These problems are really easy. You're not even working with a curve anymore. Despite how confusing it might look at first, once you get the hang of it, you're going to love when you see these problems on the exam. And again, that's where the best affordable bundle is, where the marginal rate of substitution is undefined. Another one where you cannot use calculus, and this one can be a little more tough, especially as you get to later in the course, and we'll see more advanced situations, but it's the case of perfect substitutes. Essentially, while both of the lines you're looking at here are going to be linear, we're looking at the best indifferent curve given the budget constraint, and the best affordable bundle at which the marginal rate of substitution is again the same slope for the Cobb-Douglas example. So your slope isn't going to change there. However, you do need to understand, and again, I can help visually to just throw this into your graphing calculator, that is either going to occur, your optimal bundle is either going to occur on the horizontal or the vertical axis, being either good 1 axis or good 2 axis. So you have to figure out which of the budget lines or which side of the budget line is actually going to intersect with while being the furthest out. So you're either going to see something here where it intersects there, and then you've got your marginal rate of substitution being -1, where your utility function is this line just running down. Or if the slope of this is a little bit greater, we're going to see it intersect on the good 1 axis as well. And in this case, you're just going to buy all of good 2 as opposed to buying all of good 1. You're not buying both goods in some sort of combination. You're just buying one good or the other in perfect substitutes. So in terms of what we're going to be looking at later on, you should understand that consumers maximize their utility subject to their budget constraint. The highest indifference curve attainable given the budget is the consumer's optimal bundle. And when the optimal bundle occurs at a point of tangency between the indifference curve and the budget line, this is called an interior solution. So that's what we just saw with the perfect substitutes case. If the relative price of one good is too high and the preferences are quasi-linear, the indifference curve will not be tangent to the budget line, and the consumer's optimal bundle occurs at a corner solution. So again, this is just going off of what we just saw with the perfect substitutes case. This one can be a little tricky just in that it seems easy, but if you just kind of gloss over it on the exam and you move too fast, it's very easy to make a mistake on this one. But at the same time, there are really only two possible answers, assuming that you got the budget line, the budget constraint correct, which pretty sure everyone in the class can handle. So once you're past all of these special cases, you can just completely rely on calculus, which is maybe a few years ago would have sounded intimidating, but it's very easy right now simply because we know how to take the marginal rate of substitution, technical marginal rate of substitution, whatever your prof calls it. But this is the problem that you're going to be optimizing. You're looking to maximize your utility of these two goods such that Y, being your being your budget constraints. We'll see that denoted M sometimes, just how much money you actually have to spend on the goods, is equal to the quantity of good one times the price of good one plus the quantity of good two times the price of good two. And the optimum, or the point of optimality, is expressed via the graphical analysis where the marginal rate of substitution equals your price of good one divided by your price of good two. So now we're just going to go over a couple of questions. Again, these are from the 2017 exam. I'll just walk you through them really. We can check out the answers as well. So the first one is just, and these are actually some of the easier questions that you would see on the exam. The second one, the question B, we'll go over in a second, is a bit harder, but this one's pretty standard. So I would not be surprised if you got something like this because it is the textbook case for this type of problem. So we have Anne taking microeconomics with professor choice, and professor choice gives 3 exams and he marks each exam out of 100 points, dropping the lowest score among the 3 exams, and gives each student a grade that is equal to the average score of the other 2 exams. The higher Anne's grade in microeconomics, the happier she is. So that implies the utility function, right? Thus, given any 2 sets of midterm scores, Anne is able to compare them. So that, first of all, satisfies the ordinal concept of utility. So we can just equate that with utility right there. And at the same time, we have everything else that we need up here to figure out what we're going to do. We'll combine that with part 1. So suppose Anne got 70 on her first exam. And we're just going to denote first exam as X2, or excuse me, second exam as X2, third exam as X3. And we're going to draw her indifference curve for the scores on the second and third exams, given that it passes through these scores. So we also know that she got a 70 on her first exam, 60 on her second, and an 80 on her third. So I'm going to switch over to the answer here if I can figure that out. Here we go. know if that worked. Are we good?
Yeah, it's good.
Thank you. All right, so for question A, we're going to lay out the optimal choice problem. So we're just going to set that utility function as a function of x1, x2, and x3 to be the grade. And we're going to do this, we're going to say maximize this such that we have half of x1 plus x2 if x3 is less than x2 and x3 is less than or equal to x2. And what we're doing there just goes back to the fact that we actually get to drop our lowest grade. So this helps out the problem a lot. Otherwise, it would be a lot more difficult. And again, just as the second part, in case she scores higher on x2 and x3 than she does in x1, it's the same exact problem except incorporating the new concept. So we know that U is either going to incorporate one of these two functions, and we already know that her lowest grade is going to be on exam number 2 because she got a 60. So we'll set the grade for 1 to 70, and then we'll set the grade to 3 for 80. And once we plug all of this into the utility function, it's going to look something like this. At which point, you're just going to fill up the rest of these. You're just populating the functions that you laid out before, and then you can actually go and graph it. Once you do that, this is what you're going to get. You'll see grade right there, score 80. So that's her score on the third exam, and then we'll also see the score 80 right there on the third exam as well. And again, because of the situation for this problem, you're just going to draw this line right here, and we're always going to see the point of intersection right there as a function of this line. So that just goes back to the similar concept of what we saw in perfect complements. Yes. So if we go back, the second question is another easy one, is Anne's preferences. Are Anne's preferences on the exam score strictly monotonic? Are they convex? And then we have to explain. So when you get a question like that, you have to state your answer and then have to back it up with some sort of mathematical explanation. So these are obviously not going to be monotonic, and I think it's pretty clear that they're not convex either. So basically, once you have something like that, and because we don't have a formula for monotonicity or convexity, whether that be weak, strong, or normal, we just have to give an example that contradicts what the property actually states. So here we would just give an example, that being if she had scored 70, 60, 80, and 70, 70, and 80, they both yield a grade of 85, although the second bundle has strictly a higher score in the second exam. So that contradicts monotonicity. And if we head over to preferences, you can kind of see immediately, just by looking at the graph, by the way, it's pretty clear to tell. Like for monotonicity, we know that it's always going to be sloping downwards, and it has to be increasing in slope. And then for convexity, we know that if we're going to draw a line between any 2 points, it has to be at least as good. So theoretically, for this to be monotonic and convex, it would have to look more similar to the Cobb-Douglas utility function, just sloping upwards like that. Well, downwards, but increasing in slope like that. So obviously the preferences are not convex. If we consider a case where she got a 70 on the first exam, a 0 on the next, and then an 80 on the last one, and compare that to if she got a 70 on the first, 80 on the second, and a 0 on the last, they both lead to a grade of 75. So that directly contradicts convexity, both strong, weak, and normal. So that's not an issue in terms of what he actually asked. And then we can just plug that into the formula and show that this leads to a final grade of 75, which is going to be greater than a score of 55, or a score that leads to a score of 55, which is going to be less than a grade of 75. So if this was to be convex, we would get an answer after plugging in and solving for that function. We would get an answer at least as good as 75 for normal convexity and stronger than 75 for strong convexity. So now I'm going to switch back to the next question. Let's see. There we go. This gets a little tougher. It's going to be a much longer question. So we're going to go with Bob consumes pizza and beers. Those are Bob's 2 options. His utility function is given 20 times the natural log of good 1 plus good 2, where good 1 is pizza and good 2 is the amount of beer he consumes. And the prices for pizza and clothes are going to be P1 and P2 respectively. So Bob has an income of $M, and the first thing we're going to have to do is find Bob's Marshallian demand curve function for pizza and beer. So again, that is his optimal choice, given prices and giving his budget constraint. So Marshallian demand, honestly, if you get confused on one of these questions, first thing you should do is just solve for the Marshallian demand function. You do enough practice, you'll just memorize that process. So I'm gonna switch over to the answer now, and we'll go over that. All right, so we'll go to question 2 now. We're going to set up our utility function, write out our marginal rate of substitution, and then once you have that figured out, you're just going to apply this marginal rate of substitution, equate it to the prices, and then plug it back in. 1 second. Got a better process for that here. Here we go. So the constrained choice problem. By the way, would it be helpful, because I have a bunch of notes from last year, would it be helpful for me just to upload my notes as well? Or is Lander good enough at actually outlining what you guys need to know? My handwriting is terrible.
You could upload them.
All right.
That'd be great.
Sounds great. You guys can try to read that.
You.
Yeah, have fun with that one. So basically, to determine the optimal bundle, one must complete the constraint choice problem, and this can be solved with calculus via basic optimization, or it can be solved algebraically with the optimization condition. The optimization condition being this right here, your marginal rate of substitution. The condition just satisfies the slope requirement of tangency, so we're basically just setting the marginal utility of good 1 over the marginal utility of good 2 equal to price 1 divided by price 2. So your left-hand side of that equation comes from your utility function, whereas the right-hand side comes from your budget constraint. So once we have that set up, obviously the slopes are going to have to be equal at that point, but we still have to actually figure out where they're going to intersect and be tangent to each other. So that's what we have done right here. We've just set the optimality condition where the solution is an interior solution. And then after that's done, that is, yeah. So no, they just got it solved right here. So 20 times P2 or X equals 20 times P divided by P1. So this is going to be your Marshallian demand function, right? So you have the optimal choice for good X1 as a function of your prices and as a function of your budget. And then you also have it for X2. So once you have that set up, you can plug in any other situation that he gives you. I know it's also pretty easy just to solve straight for the numbers themselves, but if you end up solving straight for the numbers and not actually yielding this formula, if he asks for you to like actually change something, you're going to be screwed when you try to go back. You're just going to run out of time. I know people this has happened to. Just solve for the formula. It's a pain to go through the algebra, but you should probably just find the Marshallian demand function. And it's also important to note, at least for Prof. Zoo, that the demand functions are only valid under certain conditions. So for example, here we need a budget divided by the price of good 2 to be at least as great as 20. Otherwise, it is not a valid function, and we don't get an acceptable answer in terms of what we understand to be a acceptable choice, right? Because you can't go with like a negative amount of a good 2. If it's above, or excuse me, if it's below at 20, you'll see it over here, then it just goes negative. So we have to flatline that either horizontally or vertically. So after you've done part 1, exactly. So now he's going to give you different variables. So now we suppose that instead of now we suppose that we have a income of 200. So that's going to be M equals 200. And then we also have a price of good 1 equals 10. And then we have to derive Bob's demand curve for beer. And that's what we have over here. So again, we're just going to lay it out. We're going to put together our Marshallian demand functions. We're going to plug in. And again, you'll be able to see if you just plot that on your graphing calculator that this right here is the exact function derived from the Marshallian demand curve. However, once our 200 divided by the price of good 1 exceeds 20, you have to flatline that vertically. And the same exact thing is going to happen down here on the horizontal axis as well. So you're definitely going to want to write that out and probably graph it as well if you want to make it easier to remember for the remainder of the problem. If we move on to part 3 now, we suppose that price of good 1 is 10 and the price of good 2 is 5. And we have to draw Bob's Engel curve for pizza and beer. You guys have covered all of this, right? Not just demand curves. All right, great. So we move on to part 3, write out our new variables again, and then we're going to just plug it into the same exact Marshallian demand functions. And then again, you're just going to graph. So once you have the Marshallian demand functions, everything has become pretty simple. You just have to memorize the actual relationships between the variables and the graphs that they produce. So if you just write this out by hand, it'll be pretty easy to like recognize what's actually going on there and what type of graph it is. So once we've done that, we can move on to part 4, where he has again changed the prices and our budget. We're looking at a price of good 1 of 10, price of good 2, or excuse me, he has not changed them, but now we are looking at a case where we have to apply a 60% sales tax on beer and then recalculate what Bob's best affordable bundle is. So again, we've got the price of good 1 is 10, price of good 2 is 5. The budget constraint is $200. But now we have to account for the fact that there is a 60% tax. So if you're going to see something like, you might get a case with excise tax or ad valorem tax, you just have to understand what part of the equation that is actually going to change. Is that going to change the price of the good, or is it going to affect the total budget constraint that we have? So in this case, we're just applying it to the price of the good because this is the pre-tax price. Once you've applied that, and then you're incorporating your tax rate, you just plug it back to the formula and you can recalculate again. So you're looking at a new formula of 5 times 1 plus 0.6 equals 8. So your price of good 2 has increased, but your price of your pizza has stayed the same. So if there was a case where you were applying 60% tax, what was it? Yeah, was it 60? Yeah, 60% sales tax. You could apply that to both pizza and beer. Then you could just do the same exact thing and apply it to your so you would multiply your budget constraint by 1 plus 0.6 times 0.6. So once you've done that, once you've incorporated the cost of the actual tax itself, again, you're just plugging it right back into the Marshallian demand function. You're calculating everything that you need to know. So this is your optimal bundle. And then once you've done that as well, if you want to calculate how much tax you've actually paid, now that we know how much of each good that we have, so we got 5 beers, right? So that's changed. We're just multiplying it by the tax rate, or the amount of income that is generated from each one of them, each sale, and that's going to be a tax, or a total tax revenue to whoever's doing the taxing, the government, of $15. This will be the last thing that we cover for today, and that's going to be part 5. So we're just going to let T be the amount of tax that Bob pays in question 4. Yeah, this was another very common one. If you look back, like on the past 5 midterms, at least Lincoln or Professor Zhu gave a problem exactly like this on every single one of them. So this is why you have to go back and relook at old midterms. Maybe you can find, have you guys used websites like Course Hero? I know there's another website that's specific to McGill. I can find it, I'll send that in the chat as well. That'll be good stuff, probably the most helpful thing you can do at the moment. Suppose that the government decides to abolish the sales tax of beer and replace it with a lump sum income tax. So when you have a lump sum income tax, immediately think that you're just subtracting from your total income or your total budget constraint. So if you have something that's being applied per unit, or ad valorem, excise tax, that's going to affect the price of each good. If it's a lump sum income tax, it's just going to affect your actual budget constraints. So that would be your variable M. So we are going to be using the, total tax revenue from the previous case. That was $15, and we're going to be offsetting your lump sum income tax. So that's going to be your value for M, 200 minus 15. So that's your total income that you're now allowed to spend. We just want the total welfare generated by the government to be exactly identical. As well, prices for both goods and the value for M remains the same, and we have to recalculate Bob's best affordable bundle. So we can do that here with 5. So again, our new value for M, or our new value for the budget constraint, is just 185. And this is the same exact calculation once you've done that, and the same exact calculation that we've done every single problem for every single part of this problem. And then the last part asks for, does Bob prefer the sales tax in part question 4 or the lump sum income tax in question 5? Yeah, no, props, love this one. So once you figured that out, you're going to just rederive, plug back into your Marshallian demand function, derive this optimal bundle, and then you're going to be comparing your optimal bundle from part 5 with the lump sum tax. You're going to be comparing that lump sum tax with the, the excise tax of question 4. or your tax rate from question 4. So basically you're just going to take the optimal bundle from question 4, plug it into your utility function, get the utility, and then you're going to take the optimal bundle from question 5, do the same exact thing, plug it into the utility function, get the utility, and then compare them with each other. So in this case, we're looking at the lump sum tax being better off. So if you got a word question like this, you would argue that the government should do a lump sum tax. That way it optimizes both the amount of tax revenue that they get being the same amount and the welfare of its citizens. That's something you will cover more in depth with a professor in the second half. I assume that you guys will have Professor Dutta, who's amazing, by the way. Prof Dutta is the best. All right, that's all I've got for today. If there are any questions, just let me know. I will stay on for a few minutes. I also know that there are
Possible for you guys